Okay. So, the background here is this perturbative approach to quantum field theory. So yeah, this is kind of a particular approach to trying to describe interactions in quantum field theory that the theory has been sort of uniquely reliant on throughout its history. And the basic strategy is to separate our Lagrangian or our Hamiltonian into a free part, which can be exactly solved, and then an interacting part, which you're kind of adding on to this exactly solvable theory. And then to try and describe interactions, express the observables of the interacting theory in a series expansion in this coupling parameter lambda, which is basically telling us how strong this interaction term is. That should be a lambda. I thought I got rid of all the G's. Apparently I failed on the train. Yeah, so we've got some quantity that we're interested in, some scattering observable or something, and we express that as a series expansion in this quantity lambda, and then the hope is that, well, the usual calculation strategy is if the interaction is relatively weak, then the first few terms of that series will provide a good approximation of the observable we're interested in. So when it comes to kind of the foundational side of this approach, there's one set of problems that are very well known and have been discussed in the literature, the philosophical literature, quite a bit, which are these sort of divergence problems that appear. So these have to do with when we sort of look at one of these coefficients in this series. To calculate that, we have to evaluate some integrals over dimension space, or over space. And if you do this naively, the way it's sort of set up in textbooks, then you arrive at divergent integrals. Specifically, what are called ultraviolet and infrared divergences. So these are divergence problems that has to do with the very high energy structure of these integrals or the very low energy structure of the integrals. And as I said, this is, well, this was kind of the most discussed foundational issue in quantum field theory, really, because this was what led to a big crisis about the consistency of the theory originally in the 1930s. And there's been a lot of literature about how to handle this and how to think about the renormalization methods that were developed to deal with those problems. But in this talk, I'm going to be focusing on a second issue that arises with this perturbative treatment of interactions. And that's that even after these issues have sort of been dealt with by renormalization, once all of the coefficients of the series have been assigned a finite value, we have very strong arguments for thinking that they're going to grow factorially, essentially. So the series as a whole is not going to have a convergent sum. So yeah, even after we've dealt with one set of divergences that are occurring in each coefficient, we get another divergence problem, essentially, when we consider the large order behavior of this expansion. And that's what I'm going to be focusing on today. And the way I'm sort of going to be setting it up is kind of like an idealized historical story. Thinking of this in terms of an oscillation between two different responses to the problem. So on the one hand, a very pessimistic take, which basically says kind of, okay, the series diverges, that means this whole formulation is foundationally irrelevant. We need to develop an entirely new approach to quantum field theory. And this is sort of one way to think about the motivation for the axiomatic approach to quantum field theory, for instance, which philosophers have talked about quite a bit. What I'm going to be kind of drawing attention to is the existence of another view, which could be characterized as a much more optimistic position, which actually takes the divergence of the series to be a source of information about quantum field theory, so a way of actually responding to the foundational worries about the theory. So that's the kind of idea I'm going to be trying to to get across this, these sort of ideas about Borel summation, instantons and renormalons, which sort of lead to an idea of the divergent large order behavior as actually containing non-perturbative information which is needed to complete the theory. Yeah, so as I said, this is sort of going to be a vaguely historical story, but it's not very good history. It's more a kind of philosopher's version of history. So yeah, we're going to kind of go through different periods, like the origin of this more pessimistic view, so when people first realized that the series diverged and the kind of reactions they had. Then the beginnings of like, okay, maybe there's something more interesting going on here. The divergence of perturbation theory actually is related to non-perturbative effects in interesting ways. I know kind of pictures developed there in the context of quantum mechanics models, so simpler cases from the full QFT case. Then kind of new pessimism coming back to QFT and realizing things are more complicated there. And then this sort of like contemporary, slightly wild mathematical physics stuff that I'm going to touch on at the end. Okay. So the first phase, as I was talking about earlier, the ultraviolet divergences were the sort of big problem in the early days of QFT. And in the late 40s, renormalization methods were developed by people like Freeman Dyson. And Dyson was actually hoping that once you renormalize perturbation theory for QED, they were interested in quantum electrodynamics at the time, that series would converge, so you'd be able to actually use this new formalism to extract exact solutions. But Dyson and other people in the early 50s sort of came up with arguments for thinking that's not the case, and the series probably diverges for interesting quantum field theories. And yeah, as I said, this kind of led to an initial sort of pessimistic reaction. So basically, kind of perturbation theory is a dead end. We've got to develop some kind of new, fully non-perturbative methods to address foundational questions about the existence of solutions to realistic quantum field theories, whether quantum field theory as a whole is even a consistent theory. Okay, so yeah, Dyson, as I said, was originally very optimistic. He was hoping to prove that QED perturbation theory converges, and he viewed that as kind of would be a demonstration of the consistency of QED. But he ended up publishing an argument in the opposite direction in 1952, and this basically led him to abandon quantum field theory and high-energy physics shortly afterwards. His argument is kind of interesting. It's not. It has a kind of not fully rigorous sort of qualitative character to it, but some of his ideas end up getting taken up later on, so it's interesting to talk about it briefly. So basically what Dyson argued in this short paper in 1952 was, he said, like, suppose we're doing a perturbative expansion for some quantity f in QED. If this is going to be a convergent expansion, it has to be, and E squared is the QED charge or something. So that's your expansion parameter, your coupling parameter that's telling you how strong the interaction is. The expansion in E squared is going to have to be analytic in some finite radius in the complex plane. So we need to think about not just real values of E squared, but negative and complex values. But he argues that if we consider a theory with negative E squared, that theory is going to be an unstable theory. So the potential is going to be unbounded from below, and you can have sort of you can group together clumps of electrons to produce negative energy states, basically. So yeah, the picture is we're in this negative E squared theory. We should have tunneling from the usual vacuum to this kind of negative energy state. And Dyson basically says, and this kind of tells us that our observable can't be, it's going to have a non-analyticity at E squared equals 0. So at the point where you move over from a stable theory to an unstable theory. As I said, this is a bit of a quick argument, I would say. It's not entirely clear to me that this would necessarily imply that all quantities in the theory are non-analytic. You could conceive of some kind of observable that is independent of whether the potential is stable or unstable. But we're going to look at some examples. So crucially, this does definitely apply to the ground state energy or the vacuum energy. So when we think about an unstable theory, it doesn't actually have a real spectrum, essentially. It'll have its ground state energy will have an imaginary part which tells you the rate at which you have tunneling from this like false vacuum to this this negative energy regime. And so when we go from the positive E squared case to the negative E squared case, you're going to have an imaginary part that like pops up basically at E squared equals 0, and that's, you know, a non-analyticity basically. And so quantities like the ground state energy and anything which is related to ground state energy are definitely not going to have a convergent expansion. So that's sort of Dyson's thinking. Shortly afterwards, there was a different set of arguments that were developed, which were essentially much more formal diagram counting type arguments. So we can represent this perturbative expansion in terms of Feynman diagrams. And Hurst and Tiring both came up with very similar related arguments. Looking at this phi to the 3 theory, they basically just chose that because it has a very simple Feynman diagram structure, and you can count the number of diagrams at each order much more easily than you can with realistic, interesting theories. So this was kind of a toy model argument. They come up with a bound for the perturbative coefficients, and the key thing here is that it's growing factorially. So you have like an n factorial coming into this bound on the coefficients, and yeah, a factorial series is obviously the sort of prototypical example of a divergent expansion. Just a note here, this phi to the 3 theory is also unstable. It has its potential isn't bounded from below, so there is like a connection here to the Dyson argument, but they didn't really point that out at the time. This was kind of a purely formal kind of diagram counting approach. And so the conclusions that came out of these papers weren't viewed as completely decisive, but the kind of view that emerged was quantum field theory perturbation series are probably asymptotic expansions rather than convergent expansions. So this is kind of like an alternating factorial type series. So you have sort of apparent convergence in the leading orders, but then if you keep calculating higher and higher terms, the factorial growth starts to take over basically, and the partial sums converge to infinity. So this is kind of what they were imagining QED perturbation series would look like. They're going to give, you know, they do display convergence in the first few orders, but then eventually at very high orders, things are going to diverge. And yeah, so in a way, from a calculational perspective, you can, you know, asymptotic expansions can still provide good approximations in their first few orders. But from a foundational point of view, many theorists, as I said, basically concluded that, okay, this really shows that perturbation theory isn't going to be able to answer the kinds of questions we want to answer. So we want to know, does QED have exact solutions? Is quantum field theory even a consistent framework, or is there still some kind of inconsistency that people had worried about from the beginning since the ultraviolet divergence issue? And so you have people like Arthur Jaffe saying, well, let's read this quote. So he writes a paper in '66 kind of giving a more rigorous version of the Hurst and Tiring arguments and expanding them a bit. So these kind of diagram counting arguments. And he concludes from it, some approximation scheme more sophisticated than perturbation theory must be used to investigate solutions of the field equations. So yeah, this is kind of the pessimistic conclusion that I was talking about earlier, that basically perturbation theory is a kind of dead end And this then motivates, or is one of the important motivations for axiomatic QFT and constructive QFT, which try to develop the theory in a fully non-perturbative way that doesn't use this series expansion at any point. Okay. And I guess this is kind of maybe one of the dominant views still in philosophy of physics, is this kind of fairly dismissive view of perturbation theory. But yeah, so what I want to draw attention to with the rest of the talk is kind of another strand that sort of picks up and develops a more optimistic take on the divergence of perturbation theory.
Can I just ask quickly, when you said foundational on the previous slide, is that like with respect to kind of conceptual, almost like philosophical issues, or were they kind of thinking practically like we just can't do calculations, and so this is not?
Well, in the 50s and 60s, there wasn't as big a, so there were then separate reasons for thinking perturbation theory was going to fail calculationally, because they thought the strong interaction was strong, and therefore perturbation theory wasn't going to provide good approximations in its leading orders. And so even the more phenomenologically orientated people thought we need to move away from perturbation theory. So there was kind of a parallel, sort of convergence between the more mathematically orientated people and the phenomenologists. They were both saying we need to get away from perturbation theory. Then when QCD comes in, things change, and the ways part, I suppose.
Right.
But I'm mainly, I'm being a bit loose about what I mean by foundational, I think, but which is something we can talk about. But
So you mentioned the strong interaction. The strong interaction would be expected to affect at some decimal place the claims of QED start to be wrong empirically at some decimal place because strong interactions start being open stuff. But if I understand the non-convergence, like the higher order terms will be messing up the empirically well-tested domain as well, because they're just very large. So is it just we're expecting, this seems to say something stronger than the strong interaction should change to the 10th decimal place. You run the series long enough and it starts changing the first decimal place, right?
Yeah, it would. If you had an expansion like this and you keep going, you're going to get a worse approximation. You're going to start to get like divergence away from your initial sort of asymptotic limit. But the thing is, so Dyson gives an estimate of how many orders it will be before QED starts to diverge, and I think it's like 30 orders or something. So we're never going to be able to calculate that far, practically speaking, for a theory like QED. It becomes, when you get to QCD, this issue kind of has a bit of a resurgence, because people start to be worried that maybe you'll have something that looks more like this, basically, and you will actually start to make your approximation worse by calculating as a fourth order or something like that. So then it starts to have more of a practical relevance again. But for QED, the argument is, this will happen, but in the very large order behavior, and we have no computational access to that. And we're going to be truncating anyway, so Should I keep going?
Also, what's the difference between the attitude shift and attitude shift 2? Because I would have thought the non-perturbative physical effects would have exact solutions. Would be exact.
Yes, so these two are going to be related. So what I'm going to move on to talk about this phase that starts in the 60s into the 70s, where there's kind of a new wave of work on the large order behavior, more looking at actually quantum mechanics models rather than quantum field theories. And they developed a view of according to which there's kind of a correspondence between effects like tunneling, which don't crop up in perturbation theory at each order, and the large order behavior of the expansion. So this is kind of the first point, essentially, that the divergence of perturbation theory, it's not just a kind of formal, like, oh, that's annoying that the series diverges. It's actually related to physical effects which are non-analytic in the coupling, and so we can kind of give a physical interpretation of why the series diverges. And then this is more about the Borel resummation techniques that I'm going to talk about. So there are ways of assigning a sum to a divergent series. And some of these quantum mechanics models, basically, they display the behavior of the earlier QFT arguments, but they're actually Borel summable. And so you can extract exact solutions.
Borel what?
Summable, resummable, or summable.
Resummable, what does that mean?
I'll talk about it.
Let's listen, please, Karen.
Yeah. Okay, so yeah, as I was saying, so the sort of intuition that comes out of this this work in the late 60s is that perturbation actually diverges for a reason. It's not just, as I was saying, a kind of sort of defect of the mathematics. It actually is tied to important physical effects, which are signaled by terms which are non-analytic in your expansion parameter. So terms like an exponential of 1 over lambda, that's the form that these sort of what are called intrinsically non-perturbative terms are often written in. So basically, this sort of term, if you do a series expansion, you just of this, you would just get zeros basically. So it doesn't appear in the series expansion at each order. It's just kind of invisible from the point of view of the perturbative expansion. But it's going to be linked to the large order behavior. So the divergent large order behavior is kind of tied to these sort of non-perturbative terms. So yeah, as I was saying, these authors sort of actually start off by analyzing quantum mechanics models rather than quantum field theories. What are called anharmonic oscillators. So these are kind of generalizations of the harmonic oscillator, where you add an additional higher order term to the Hamiltonian of the harmonic oscillator. And they can be understood as sort of one-dimensional analogues of scalar field theories, basically. So this 5 to the 3 model that I was talking about earlier, and the 5 to the 4 model, the sort of standard textbook sort of toy model of QFT. And yeah, what these sort of studies demonstrated was that the large order coefficients, so kind of the rate of the factorial divergence at very large orders, is quantitatively related to the imaginary part of your observables at different values of the coupling constant. So, for instance, negative values or complex values. So again, we're talking about considering the whole complex plane rather than just the sort of physically relevant case of a real positive coupling. So yeah, so this is a quartic anharmonic oscillator model. So this is the usual sort of Hamiltonian of the harmonic oscillator, and then we've added on an additional term that's quartic in the position, which can be sort of viewed as an analog of the 5 to the 4 theory in one dimension. It turns out if you try to write a perturbative expansion for the ground state of this model, in the same way that I was talking about earlier for QFT observables, this is a divergent series. And we can sort of see why it's a divergent series in a way which has some analogues to this argument that Dyson had earlier for why QED perturbation theory diverges. So this is the sort of potential of the quartic anharmonic oscillator. If we consider the case where the coupling constant is taken to be negative rather than positive, you get a potential that looks like this. So it's an unstable potential, it's unbounded from below. And this means that the ground state energy picks up an imaginary part, which essentially parameterizes the rate of decay of this sort of false ground state. So the decay rate to negative energies. Bender and Wu, in their sort of classic paper on the anharmonic oscillator, they calculate this imaginary part using a different approximation method, the WKB approximation, which is kind of a semi-classical approximation method. And yeah, end up with an expression for the imaginary part of the ground state, which is non-analytic in lambda. So this the coupling that we're normally doing an upperturbative expansion in. What they then do is use what's called a dispersion relation to relate this imaginary part of the ground state energy to the real part. Then perform a sort of another perturbative expansion inside that integral and end up with an expression for the perturbative coefficients, so the coefficients of our expansion in lambda in terms of this imaginary part at negative values of the expansion parameter. And then if you plug in this WKB approximation, you get a quantitative prediction for the large order coefficients. So this A here is like the coefficient on this this non-perturbative, intrinsically non-perturbative contribution to the ground state energy. So the idea here is that tunneling effect, so this kind of tunneling from a false vacuum or false ground state to the negative energy, that physical effect is not captured within perturbation theory at each order. But there is a quantitative connection between the parameters of that tunneling, the sort of parameters describing that tunneling effect, and the large order coefficients, so the divergent large order coefficients. And yeah, this gets built on, this sort of idea gets built on and taken into the quantum field theory context by people like 't Hooft and Sint-Justin. And they sort of deepen this semi-classical approach to the large order behavior, bringing in this notion of instantons, which kind of, comes from QFT, but then is also applied to quantum mechanics models. I'm not going to talk about this in detail, but basically the instantons are kind of saddle points in your action, which can be taken to correspond to tunneling events between local minima. So you'll expect to get instantons, these saddle points in the action, in the Euclidean action specifically, when you have an unstable potential, or you have a potential like a double well potential, say. So you have two minima, and you expect to have tunneling between those two minima. And yeah, so this instanton language is used to sort of expand on this semi-classical calculation of these tunneling effects, which Bender and Wood employed, and use the coefficients of these instanton coefficients to approximate the large order coefficients, so the divergent factorial divergences that you'd expect in your perturbative expansion. And we can sort of, this is the Borel resummation approach that I mentioned earlier in answer to Osmar's question, which, I'm going to give a brief introduction to. So this is kind of another formal tool which is used to develop this more optimistic view of the divergence of perturbation theory. So the key idea with the Borel resummation framework is that we can actually extend the standard notion of a convergent sum, so we can generalize it. Borel resummation is viewed as the most powerful way of doing that, so we want some kind of generalization where if we take a normal convergent series, we get the usual sum, but we can also assign a sum to a larger number of series which don't have convergent sums. So it's sort of a conservative extension of the standard notion of a sum. So the key idea is this notion of a Borel transformation. So we start off with our perturbation series. The Borel transform is this series essentially. So we've kind of factored out a factor of n factorial. So Borel resummation is our tool for understanding factorial series essentially. And this thing, the Borel transformation, it turns out to be a very powerful source of information about the behavior of our original series, and in particular the sort of the analytic structure of this thing, the Borel transformation, tells us about the large order behavior of this thing, our original perturbation series. So singularities in the Borel transform are related to patterns of factorial divergence.
So Z is a complex number there, whereas
yes,
is a real number. Right?
Yes, and that's also, so we're also going to be considering analytic continuation to complex Z, and that's crucial as well. We need to think about the entire complex plane here. Yeah, and one of the of course, another big motivation for this idea of the Borel transform is that we can then use it to define a sum, which, as I said, will sort of extend the range of series that we can assign sums to. So essentially, this Laplace integral over that's the Borel transform again. I'm not going to go through it in detail, but if you start with a convergent series, that's always going to give you the same thing as the convergent sum. But it allows us to assign a sum to some divergent series. And another key idea here is that, I think I've already said this actually, singularities on, so the singularities of the Borel transform tell us about the behavior of the series, the large order behavior of the series. Most of those are going to be fine. So here we're integrating from 0 to infinity along the positive axis. It's called the positive Borel axis a lot of the time, because we're talking, they use that language when they're talking about the Borel transform. If you have singularities on the real axis, then the positive real axis, then that is a problem for the definition of this sum. Because we're going to hit a singularity when we integrate from 0 to infinity. If there are singularities on the positive z-axis of this Borel transform, then this integral is, at least prima facie, not well defined, and the model is said to be non-Borel summable. You can consider further generalizations essentially of the Borel resummation approach, where we consider sort of deviating this Laplace integral around the singularities that might appear in your Borel transform. But crucially, when you do this, you're going to pick up a kind of ambiguity, essentially, depending on whether you go above or below the singularity. And these kind of ambiguities are related, again, to this intrinsically non-perturbative part of your observable. So essentially, if you have singularities on the positive axis, your series is not Borel summable in the usual sense. You can then try and take a contour around it, but you're going to get this sort of non-perturbative ambiguity in your definition of the Borel sum. So just to kind of give some intuitions here about this Borel transform, because it's quite important for understanding these ideas. As I was saying, singularities on the Borel transform are related to the rate of factorial divergence and the type of factorial divergence you see in the large order coefficients. And it's helpful to sort of look at a couple of simple examples. So if we have an alternating factorial divergent series, so this is with a -1 to the n, and we try and take its Borel transform, you essentially have when you take the Borel transform of this series, you're dividing by a factor of n factorial, so you end up with kind of a geometric series essentially, which you can assign a convergent sum to, and you get your Borel transform having this form. So it has a pole on the negative axis of the Borel transform. So this, you can assign the Borel sum integral, this thing, should be well defined for that kind of series. So when you have an alternating factorial series, there's no big problem. But if you, change to x's instead of lambdas. I thought I'd got all the notation consistent, sorry about that. Pretend those x's are lambdas. If you have a fixed sign factorial series, so a series which just diverges like n factorial, and you do the same thing, you take the Borel transformation, you get 1 over 1 minus z, so you have a singularity at z equals 1, so on the positive axis, and that means that the Borel transform of that series is not well defined without running into this issue with ambiguities where you take your contour around the singularity. So basically the message here is alternating factorial series are okay in a way. You can assign Borel sums to them even though they're divergent. Fixed sign factorial series are more problematic. So one thing that came out of this study of the anharmonic oscillator was essentially that all of its singularities on its Borel transform are on the negative axis. So even though this series diverges factorially, and it does so for apparently similar reasons to Dyson's argument for why QED should diverge, it's Borel summable. So we can actually, using Borel summary summation, we can extract the exact solutions of this model. Yeah, and this is basically saying that each one of these singularities can be associated with what are called instanton sectors. So each one of these singularities is associated with these kind of tunneling events from your false ground state to your negative energy state. So you can calculate each of these points on the Borel transform using these kind of semi-classical techniques that were developed, this kind of instanton language that I was talking about earlier. Yes, so how am I doing for time, Alex? I feel like I'm rambling a bit.
Well, yeah, you've gone about 35 minutes.
Oh, okay. I've gone for 35 minutes.
Yeah, more or less.
Okay. Hopefully it should get less rambly. I think that was like the hard bit. So yes, so these cumulative advances in the 60s and 70s led to important shifts in the attitude that people took towards the divergence of perturbation theory, or maybe, from a philosophical point of view, the attitude we should take. Rather than just being a kind of technical problem, it came to be viewed as kind of a window into non-perturbative physics. So you have these non-perturbative effects, like instanton effects, for instance. They're actually quantitatively related to the large order coefficients. And so, in principle, maybe you can draw conclusions about the non-perturbative physics using the large order behavior, this kind of divergent large order behavior. It has a direct relation and correspondence to these kind of effects, which are missing if you just look at your perturbation series order by order. And this kind of stuff about Borel resummation, to me at least, suggests that Dyson's argument, people reacted way too hastily to that. In principle, even if Dyson's argument does show that QED perturbation theory diverges, that doesn't show that it can't be Borel resummed, for instance. And so it might still be possible to extract exact solutions from your QFT perturbation series, even though it's divergent. which, yeah, could then lead you to a much more optimistic view. Maybe we can actually understand the non-perturbative effects which are missing from perturbation theory by looking at its large order effects, so they're kind of contained within perturbation theory, and we can even do the kind of stuff that constructive field theory people want to do, trying to find exact solutions to field equations by studying this kind of the large order behavior. The sort of problem again comes when people return to QFT. So as I said, in the 60s and 70s, a lot of this work was done on quantum mechanics toy models, which could be solved by other methods, and there were other ways of understanding those models. When we come back to theories like QED and QCD by the 70s, and ask what happens now, what happens for QFTs, things get more complicated, and new problems arise, which lead to another round of pessimism, essentially, about perturbation theory. And a return to this idea that, no, we're really going to have to go outside of perturbation theory if we want to understand these theories. So the paper I'm going to talk about here is this 1977 paper by Ed Hooft. And yeah, this is kind of a quote that's supposed to illustrate this return to a pessimistic stance. So he says, to get an accurate theory, it's mandatory to go beyond the usual perturbation expansion. Why did he conclude that? Despite these sort of more optimistic strands that had been developing in the years prior to that. In this paper in '77, he argued, he sort of discovered a new set of singularities on the Borel plane for gauge theories, four-dimensional gauge theories like QED and QCD, which he dubbed renormalons. And basically the problem is we don't quite understand, we don't really know how to make sense of these new additional singularities on the Borel plane. So one way to, basically the argument for the existence of renormalons is kind of, again, going back to Feynman diagrams and just looking at the diagram structure. So Ed Hooft, in that paper in 1977, he started to write down these bubble chain diagrams. So this is where you have an insertion of n loops inside one diagram that you have to calculate, and you can imagine just adding additional loops at each order. So we're basically considering a kind of subset of the Feynman diagrams. And each one of these loops is going to lead to a logarithm of some momentum scale. And what Ed Hooft argued is that this is going to lead to a factorial divergence of the coefficient, a factorial growth of the coefficients, just considering this subset of diagrams, basically. So I'm not going to kind of go through this in detail, but the sort of idea is that we can write down a form of the kind of integral we need to evaluate to evaluate these bubble chain diagrams. And then if we look at what happens as momentum goes very large, in the case of QED, we can argue that that integral is going to lead to a factor of n factorial at each order. And consequently, that means there's going to be, in the case of QED, that means there's going to be a singularity on the positive axis of the Borel plane. So this is the kind of bad area where we want to kind of integrate over to do our Borel resummation. Why did Ed Hooft use this term renormalon? It was sort of in analogy with the instantons that I was talking about earlier. So he sort of developed this idea that we could associate poles on the Borel transform with instanton effects, and so in analogy, he called these renormalons because they're additional poles on the Borel axis. But there is some kind of connection to renormalization here, because these kinematic logarithms that you're getting in this integral, they originate in the renormalization procedure. So you get kind of logarithms of the renormalization scale, and that's kind of, in a sense, why you get these kind of integrals cropping up. And yeah, in particular, you don't find this kind of thing in ordinary quantum mechanics where you don't have renormalization. And you don't find it also in super renormalizable quantum field theories, so theories that have kind of trivial renormalization. In 2 dimensions, for instance, the kind of QFTs that can be exactly solved. You don't find these renormalon contributions, and so there is some fuzzy connection to renormalization, but it's kind of a weird terminology. Because they're essentially just additional poles on the Borel transform of your series that you don't know how to make sense of. Yeah, so this is kind of like a sketch of what, I think this is actually the Borel plane of QCD observables, or this is, the kind of drawing that theorists do of the Borel transform. So it's got these kind of singularities on it. In the case of QCD, so the renormalons are, another reason they're called renormalons maybe is that they're related to the beta function of your theory. So the position at which you find these renormalon singularities is parameterized by the leading coefficient of the beta function that tells you how your theory scales. And in the case of QED, the ones on the positive real axis, so the important bit, are related to the ultraviolet structure of the theory, so they're called ultraviolet renormalons. In the case of QCD, the singularities are associated with the infrared structure, so they're called infrared renormalons. And then that X is an instanton, so because QCD also has a non-trivial vacuum structure, you then expect tunneling effects, and instantons are also going to kind of crop up there. Okay, so in a way, the big issue is, okay, it looks like our QFT perturbation series are definitely not going to be Borel summable. They've got these singularities and these fixed sign factorial growth, patterns of fixed sign factorial growth in the perturbative coefficients. And as I said, you can then think about, okay, maybe we could deviate the Laplace integral around these singularities. But the issue is you're going to get an ambiguity, an intrinsically non-perturbative ambiguity from the question of whether you go above or below these poles. And 't Hooft argued that these additional singularities in the Borel transform, they definitely can't be associated with saddles in the action. So we can't give this kind of semi-classical analysis which had been developed in the quantum mechanics case. So that's kind of a key part of why he viewed this as these renormalon singularities as problematic, as this quote suggests. So he says here, you're going to have instanton singularities on the right side of the real axis, but they don't destroy your hopes for obtaining a convergent theory. And essentially, his argument there is we kind of know how to make sense of those singularities. They're associated with tunneling effects, and we know how to calculate those tunneling effects and add them to the perturbative content of the theory. But with these renormalons, we don't really, the situation is less clear for these other type of singularities. That's at the end of that quote. And so, yeah, this leads to a return of a more pessimistic view when it comes to QFT. These renormalon singularities, they're going to lead to ambiguities in the Borel sum. And we don't really know how to resolve that ambiguity. So it looks like we need to bring in some additional non-perturbative input in order to give some description of these non-analytic exponential in -1/λ type terms. And the semi-classical approach that's been developed for instantons, that's not going to work. And so essentially, our theory is ambiguously defined if we're going to try and define it with the Borel transform of the perturbation series. So again, it looks like we need something new to make sense of realistic quantum field theories. And that's kind of, in a way, still the mainstream view in theoretical physics, I would say. I wanted to briefly talk about this kind of more, in a way, wild wild ideas that have come out of more mathematical physics approaches under the title of resurgence theory. So this is kind of a, as I said, originally motivated by sort of more pure mathematics kind of stuff, attempt to generalize the Borel resummation approach, and describe the situations in which we can actually assign a unique sum to series which have singularities on their positive real axis of their Borel planes. So essentially, as I was saying, yeah, sort of extend again the space of series which we can assign a unique sum to. And this has led to an attitude shift, a return of some kind of optimistic view in certain quarters of mathematical physics. I'm going to read some quotes in a second. So the hope is that it may actually be possible to reconstruct the intrinsically non-perturbative terms and resolve these ambiguities just using the large order behavior and perturbation theory alone, without bringing in any additional resources or any semi-classical analysis of the renormalization or whatever. Yeah, so this is a quote that sort of illustrates this this return of optimism. So Dune and Unseld, they say, our long-term goal in applying resurgence to QFT is rather ambitious. We aim to give a non-perturbative continuum definition of quantum field theory and provide a mathematically rigorous foundation. So yeah, that's kind of pretty optimistic, I would say. But the idea, the sort of motivation here is to go back to this correspondence between non-perturbative effects like instanton effects and the large order coefficients that I talked about when I was discussing Bender and Wu's work on the anharmonic oscillator. So as I said, they established a quantitative connection between the decay rate, essentially, of the ground state and the rate of factorial divergence of the perturbation series. And they sort of went in this direction. So they did a calculation of the non-perturbative physics. They used this WKB approximation, then used that to estimate the large order coefficients, and then numerically sort of verified that they were very good approximations. The idea with resurgence is to sort of go in the other direction. So this correspondence could actually be used to reconstruct the non-perturbative physics. So start with the large order coefficients and use that to calculate these kind of intrinsically non-perturbative effects. And yeah, it all gets pretty above my head, to be honest, like from a from a pure mathematics point of view. But it seems like the people who are trying to apply these ideas to QFT have had some successes in demonstrating the existence of such a construction for particular models. So for instance, the quantum mechanical double well potential, the anharmonic oscillator. Actually, sorry, the double well potential is more important because the double well potential has singularities on its positive axis of its Borel transform. So this is the kind of case that they're interested in, really, is like, can we reconstruct the non-perturbative physics using those singularities themselves? And yeah, this is a quote from a sort of recent paper on resurgence in quantum field theory, where Mourinho and his colleagues are saying it may actually be possible to carry out this sort of construction even lacking any sort of semi-classical understanding of the renormalization. So he says here, it's perfectly conceivable and in our opinion quite likely that for theories with renormalization in infinite volume, one doesn't have a semi-classical interpretation of the trans series, but some version of resurgence will still be valid. So this term trans series it's a term that comes in this resurgence literature where they want to talk about essentially generalizing the idea of a power series to include exponential terms which are exponential in 1 over your expansion parameter. So these sort of non-analytic terms, you add those in addition to your usual perturbation series, and then the idea is you can use that to construct exact solutions. And that there's a correspondence between the large order behavior of your original perturbation series and the coefficients of this trans series that you're constructing. Difficulties for this program. One problem is that it's basically only been shown to work in the cases where we don't need it. So it's been applied to models that are exactly solvable, for instance, or are solvable by some other method, where we have some other handle on the physics, essentially, and then we can verify that you have this correspondence and you can do this reconstruction of the non-perturbative physics from the large order behavior of the perturbative expansion. So yeah, they look at quantum mechanics models, they look at kind of supersymmetric QFTs and integrable QFTs in 2 dimensions, that kind of thing. That's not where we need it, though. We need it in the cases where we don't have those kind of additional handles on the physics. And so there's an element of conjecture, essentially, in saying, oh, maybe the same thing can be applied to realistic QFTs, but yeah, this is very conjectural at this point. In particular, the resurgent strategy, in order to do this reconstruction, you basically have to have a complete knowledge of the singularity structure of your Borel transform. And that's very difficult to get for realistic QFTs. These sort of arguments, like the renormalization arguments, they're really kind of just looking at one subset of the diagrams and trying to give an approximation of where you might get poles on your Borel transform. If you were going to do this, you'd need to have sort of complete information about the analytic structure of the Borel transform. Then there's this question about, you know, how does this relate to theories like QED, which we think they might not have continuum solutions because of the Landau pole problem. I'm not really going to talk about that. That is, I think, a big problem, to my own personal understanding, how those issues relate together, the renormalization problem and the Landau pole problem. So, yes, I'm concluding now. I think I've gone on quite long enough. What's the kind of philosophical upshot of this? As I said, I've sort of structured this in a kind of semi-historical way, and part of the reason for that is that, in a sense, there isn't a very clear philosophical upshot for all of this, because we're left in an uncertain position. These trajectories, these theoretical developments haven't concluded, essentially, and we're left sort of uncertain about how this is all going to pan out. It might seem like I've just taken you on a very windy route back to a familiar conclusion, which is that we still don't understand the theoretical content of empirically successful QFTs. We've basically just given a new formulation of that problem in terms of this language of Borel resummation. I do think that there's something interesting here. There is a kind of progress, maybe not in solving the problem, the big problem of QFT, but kind of understanding what we need to understand in order to solve the problem. One upshot I definitely wanted to stress, if that hasn't come through clearly already, is that I think this idea that the divergence of perturbation theory is just a formal sort of roadblock, that's definitely wrong. And you know, there is this interesting correspondence between the large order behavior and non-perturbative effects. And so the divergence of perturbation theory on its own, it's definitely not a reason to dismiss the perturbative framework as foundationally irrelevant in the way that people did in the 50s. The question is really, how far can we go with it? And that's where this remains an unanswered question currently. But we do kind of know that the renormalization singularities seem to be the main issue that remains for answering this question. So the renormalization singularities are the key obstacle to addressing the question of how far we can really go with perturbation theory with regards to exact solutions and the exact structure of realistic QFTs. And yeah, I'll stop there. Thank you.